recording? We're rolling. Okay. So today we're going to derive the equations for current source density and try to say how this applies to the brain or to even to EEG signals. So basically, current source density. So the problem there's something called current density. So I'll just put that up here. So versus current density. That's a different number, which I'll talk about. Current density is is J. So it's known as J. So current source density is just a number. And what this number is it basically, so we'll just sort of say it in words at the beginning, it just basically says whether there's current appearing out of the void. So that's kind of strange, but that's, is there current sort of like erupting at this point? Or is there current sort of disappearing at that point? So basically, this is a source, and this is a sink, meaning sort of something that the sink. It's like the drain. So this is the faucet, and this is the drain, and that's what current source density. That's basically what current source density is in words, and so we'll go over the equations for it. But why do we care about current source density? So current source density is basically the way to figure out what's actually happening. So if you could do three-dimensional current source density, you could actually say exactly what happened in the brain at a given scale. So depending on how finely you're sampling. So in some respects, current source density is the ground truth, what actually happened. So as we'll see, you can't, it's relatively hard to do it at very high spatial resolution, but in animal experiments, people have done it at higher spatial resolution. And there's another important thing that we'll talk about in the main lecture, which is by doing current source density in animal experiments, we can get the necessary data to really see why we want to model the cortex, activity in the cortex as a current dipole. So when I talk next week about source localization in EEG and MEG, one of the things that we see there is we model the current flow as a dipole that's going perpendicular to the cortex. And the current source density experiments that I'll talk about in the main lecture are the primary reasons why we think that modeling that as a current dipole is actually is true. That's actually sort of actually describes what's going on. Okay, so the first thing before when we're deriving the current source density is that what we're doing here is called the low frequency field approximation. So we've talked, during the semester about RF, or radio frequency. So radio frequency are very rapid oscillations in the electric and magnetic field. And so like the RF coil. And so how is that different? So that's when you very rapidly oscillate the electric or magnetic field, what happens is you get radio waves. And so if you think about magnetism, if you have a current flowing, it creates a magnetic field. But if the current is flowing and you get this magnetic field, and the magnetic field doesn't change, it's just sort of a static magnetic field, that will fall off relatively rapidly from the wire. So like if you have a wire flowing here and then the magnetic field, sorry, wrong hand. So if you have a wire flowing here and the magnetic field flows around the wire, circularly around the wire, that's a static magnetic field. That doesn't create radio waves. That just, it falls off relatively quickly. It doesn't sort of propagate away. So if you very rapidly change the magnetic field or the electric field, then what happens is you get these propagating waves that will sort of like go off through the vacuum. And so when we're talking about EEG and MEG, luckily we can basically ignore that. And so we'll show where we ignore it in the Maxwell equations. But basically our assumption is the electric fields. So the electric fields are uncoupled from magnetic. Because our frequencies are too low. Now, they're always coupled to some extent. The electric and magnetic fields are always coupled, but because if you look at the Maxwell equations, you'll see a c in there, which is the speed of light, like 10 to the 10th centimeters per second. And so that's a really big number. And so unless your frequency gets up close to that number, the coupling is so small that you can just kind of ignore it. And that's the situation with the electric and the magnetic fields generated by, and the currents that are generated by activity in the brain. So we assume they're uncoupled, and then what we can do is we calculate the electric fields as if the magnetic fields don't exist. So remember, I didn't really define an electric field. An electric field is if you have a charge, then extending out from the charge, there'll be just invisibly in space, there'll be this effect that if you put another charge there, that other charge will, depending on whether it's positive or negative, either be attracted or pushed away. So that's the definition of an electric field, whatever it is that sort of somehow fills space and has the potential to actually do something to another charge. But if there's no other charge there, then it's just doing nothing. It's just kind of like, it just goes out, but it falls off relatively quickly. So that's an electric field. And a magnetic field is the same kind of thing. So if you move some charges, you get a magnetic field, and that magnetic field is static. It just will, have an effect on charges moving through it, but if there are no other charges moving through it, it's just there. So that's the magnetic field and electric field. And those should be distinguished between, make sure to distinguish between an electric field and an electric current. So an electric current is actually charges moving as opposed to just the thing that a charge does to space around it. So we calculate electric fields as if the magnetic fields don't exist. Then you just calculate the magnetic fields because we perhaps want to do MEG from currents, from the distribution of currents. So that simplifies. And then the other thing we do is we'll also ignore capacitance. So capacitance is the ability to store charge. So there's a little capacitance in the head, but we'll just kind of ignore it. And this whole thing will make our life much simpler. And so this is sometimes called, electrostatics or magnetostatics. And that's kind of weird when you think about it. It's just like, isn't the brain dynamic? Isn't things changing? Yes, they are changing, but basically what this says is we can sort of model it as if at any instant there's a particular current at this point, and then that is just like a static effect that generates these electric and magnetic fields, and then it influences which way currents go, and then we can just go to the next time point and do the same thing as if there's no history, there's no dependence on what happened at the previous time point. So that makes it simpler to deal with. So how do we calculate the electric field? So we'll start off. So here's the electric field. So the electric field is a vector, and in all of these equations, we're assuming that this is something just for a point in space. So you could think of this implicitly as you've got an r vector here, which means that's x, y, z. So this is the electric field at a point in space. And so you could, if you go to different parts of space, you get a different electric field. So this tells how to compute the electric field for a point in space. But we'll just leave, to not clutter it up, we'll leave that out. But that's the implication in all these equations. So the way you calculate the electric field is you take the negative of the gradient. So there's our gradient. It's usually, like I said, it's usually drawn in bold because when you take the gradient, you end up with a vector. And it's taking the gradient of this capital phi, which is the potential. That's the voltage at a point in space. So remember, this guy turns a scalar into vector, and this guy is basically the potential voltage, which is a scalar. That's just a number. It's kind of like how much pressure. You can sort of think of it as water pressure. How much water pressure, electrical water pressure, is there at this point in space? So if we take the gradient of that, which means the way that it's changing the most rapidly, the direction in which it's changing the most rapidly, and how fast is it changing in that direction. And then if we take the negative of it, we get the electric field vector. So this is the electric field vector. And so what does that mean? So that means the force you would get on a test charge. So this is, like I said, this is the funny thing about the electric field. It goes out, you have a charge and it does something to space around it, but you can't actually detect it unless you put something in there, another charge in there. And force, remember, force is a vector. So basically what this says is, this says how do you calculate the direction that a force would, the direction of the force that would be on a charge if you actually, if you had this particular electric field. So it also tells you, because it gives you a way of calculating what the force on a charge is, it also tells you, which way the current will go. Because current is charges, which way current will go. Depends, there's other things that will affect which way current will go, like do you have a wire or is it just air? But if there's a conductor there, the electric field will tell you, which way the current is going to flow, actually. So that's the electric field. That's how you calculate it. You calculate it by taking the gradient of the potential at each point in space. Okay, so then there's another part of it. This is the part that we throw out. So there's another part which is how rapidly is the A vector changing? So that's the part that we toss. So this guy, we ignore this. This is the one that causes the coupling because our rate of change isn't fast enough. So we then introduced another number so that we have E for the electric field and B for the magnetic field and J for the direction of the currents. Now we've got A. So what is so A is called the vector potential, and it's sometimes defined in this kind of backwards way as the magnetic field equals the curl of A. So that's sort of unhelpful. It's just like, okay, we got the magnetic field, but it's defined as the curl of A, but what is A? And another definition of A, the vector potential that you can tell from the name vector potential that it must be some vector quantity itself. And so another one that makes more sense to me is that that's kind of the backwards definition, the original sort of Maxwell backwards definition. But another definition is this thing has to do with how magnetic fields propagate through space. But basically it's the sum over a volume of all the currents weighted by what their distance away is. So it's a distance, and this is like summed across all the volume elements. So that one makes more sense to me. So it's kind of like a distance weighted sum of vector sum, because this is a current. So you've got currents going every which way, and then you've got a point here, and we're trying to figure out the A vector, and the A vector just says like how far away are those currents, and what direction are they going, and do a whole vector sum of them and get a vector here. So that's the vector potential. And if you study quantum mechanics, this is the main thing that you use. That's called the vector potential A. Okay, so after all of that, we're going to throw it out because this is the thing that causes the coupling between the electric and magnetic fields. And since we're assuming that we have a low frequency approximation because our rate of change is slow enough in this vector potential, then we can just throw it out. So if we throw it out, then we just have to do the gradient. And so this is, approximately equal to, after we throw it out, just the gradient. And so what is the gradient? So the gradient was that we still got that minus there. So it's just the minus of how the voltage changes in the x direction times the x unit vector plus how the voltage changes in the this was just trying to figure out the steepest uphill direction, how it changes when you go in the y direction plus how it changes when you go in the z direction. So this was just a way of trying to figure out what's the steepest uphill direction in the voltage. Plus 0 because we zeroed this guy out. Okay, so that's our first. That's the first equation there. So let's put a little thing around it so I can see it. I'll get it separated from those guys. Okay. So that's the first equation. So I didn't define the J, so maybe we should just sort of mention what the J is. So, one more definition. So, because we got a J here. So the J is the current density, not the current source density. And the current density is basically just equal to this constant times, so that's called the conductivity, times the E field. So this goes back to this. Sorry, this guy is related to this one. So basically, this just says. So this is the conductivity. This is Ohm's law. Conductivity. This is Ohm's law. So Ohm's law says, depending on how conductive something is, that will determine how much current is flowing and what direction it's going. So this is, which way current will go and how much. So the how much is determined by the conductivity. So this guy is the just current density. And this guy's electric field. So that's what the J is. So the J is very similar to this exact same direction as the E. Whatever direction the E field is going, that tells you the J. And then depending on how conductive the medium is, that tells you how big this is compared to E, because if the conductivity is small, then you won't have very much current. Okay, so I think we got most of the definitions there. But we're still at the electric field. We haven't gotten to the current source density, and so now the current source density. So what is the current source density? So the current source density, CSD, is the second derivative, which in space is called the Laplacian. And so what is that? So that one, now we finally get to use the divergence. So that one is basically the divergence. So that's the dot product like derivative. So the derivative operator. So this is the one that sort of tells you how radiating a vector field is at a point, or how sort of contracting it is. And that's operating on this guy right here, so minus the gradient of the potential. So this guy is a vector. So this guy is, find, I'll just say radiatingness of vectors, vector field at a point. And then this guy, remember, is a vector. This guy was a scalar. That was just a number. But this gradient figures out which way is it changing the most rapidly. But remember, this guy turns a vector into scalar. So we start off with a scalar. We take the gradient of it, which figures out which way is it going, moving the fastest. That makes a vector. And then we operate on that vector with this thing, which sort of finds out how radiating it is at each point, and that turns it back into a number. So the bottom line is just a number. So we end up with a scalar field, which means at each point in space, there's just a number instead of a vector. Whereas here, for the electric field, at each point in space, there's a vector. Or, for the gradient of the potential, there's a vector at each point in space. And so this thing, so if we sort of go through the math and take the divergence equation that we had last time and apply it to this thing, you actually get something that's pretty simple. It's just we still got the negative there. It's just the negative of the second derivative of the potential. So we have to say what is the second derivative. It's usually written here with the squared after as opposed to before. So this is plus the second derivative of the potential moving in the y direction plus the second derivative of the potential moving in the z direction. So this particular thing, this second spatial derivative, we haven't. I'll say what the derivatives are over there in a second. So the second spatial derivative is often written like this. Because it appears a lot. So that's called the Laplacian. So that's this guy's the Laplacian. So if you see that, it's the second. It's kind of weird because normally when you see this upside down delta, you figure that should turn things into a vector. But when you square it, when you do the second derivative, because of this operation here, it turns it back into a number. So this thing is just a number. Not a vector. And that's the current source density. So here's our final answer. So what is the current source density? The current source density is just the second derivative of the voltage. So this is the CSD. So what does the second derivative mean? So let's go back to the second derivative. So if we go to the first derivative, so say you have like a curve like that. So this is say the x direction. And if you go to this point, if you take the slope, that's the first derivative. So this guy is, the first derivative. Like one of these guys here, first derivative. It's just how rapidly changing is the function at that point. But if you have another function, say another function that looks, let's try to line it up. So another function that looks like this, you would get the same derivative there. So first derivative, so if we took the first derivative at that point, it's going to be the same. So it doesn't really tell us whether we've got something that's kind of concave or convex. So if we plot out the first derivative and then take the derivative of that will distinguish these two situations. And what's a quick and dirty discrete approximation to the second derivative? So approx second derivative is basically compare your value to the average of the neighbors. So, compare current point to average of neighbors. Compare meaning subtract. So let's just see how that would work here. So if I take a point over here and a point over here versus, a point over here and a point over here. So here you can see that this guy is going to be sort of less than the average of the neighbors. Here you can see this guy is going to be more than the average of the neighbors. So that's what when you think of the second derivative, how should you physically think of it? When you see this, looks like, there's all these symbols there. But the way to think of that is it's measuring the curvature. It's measuring the curvature of that point. So it's like if you go out around that point, are the neighbors on average bigger than you, or are they less than you? So that's what the second derivative is, and that's what the current source density. That's how you calculate the current source density. You basically just look at the voltages. You look at your voltage and you look at the voltages around you, and then you see whether you're bigger or smaller than the voltages around you. No vectors involved. And then that tells you whether there's current erupting from this place or there's current disappearing into this place. So that's fundamentally what the current source density is. So it's a way of actually taking a bunch of measurements and figuring out where all the currents are flowing, like where are they coming, where are they disappearing into, where are they sort of erupting out of. So how would you do something like this? So I'm going to talk about that in a lot more detail in the main lecture, but the way you would do something like this is you would just make a whole bunch of measurements. So here's a little chunk of cortex, and say it's got like a pyramidal cell in it like that. And so we want to figure out like where are all the currents going in this space. And so what would we do? Well, we would just go and measure at an instant in time. If we could just go into there and then just measure what the potential was, what was the voltage at each of those points, and then you'd have to sort of like do, you'd have to do it in 3D, right? So you can see what the problem is. So you'd have to sort of like do it throughout this entire volume. So if we could somehow do that, then what we would do at each point, how would we perform this calculation? So it looks difficult, but basically all we would do is we would just say, okay, I'll take this point, and then I'll just look around in 3D. So this is the second derivative in 3D. So you have to sort of, don't get your dimensions mixed up. So it's the second derivative, but we're doing it in 3D. And so basically we look out all around ourselves and figure out what is the potential at each of those points, average them, and then subtract them from the potential at this point. And if this guy is bigger, if the center point is bigger, then that means that there's current erupting out of this point. So if we did that calculation near the cell, we would see, like if we did that calculation over here, what we would find is that that would give us a positive number because current is, maybe the axon fired and current is sort of flowing out, just erupting out of the void right at that point. So this is the true answer. This is actually where the currents are going. It depends on how finely you did the sampling. So if you did the sampling more coarsely, you wouldn't be able to pick up the fine details, but you would pick up sort of the overall pattern of where the currents were going. And this is kind of the gold standard. This is actually where the currents really are going in this volume. So that's the current source density. So it's the second derivative of the potential field. And we get it by first taking the gradient, which turns the potential field into a vector field, and then we operate on it with the divergence, which turns it back into a field of numbers. But when you do this, the divergence of the gradient, it just boils down to the second spatial derivative. So it's the second spatial done in 3D derivative. That's what the Laplacian is. Okay, so that's the current source density, derivation of the current source density, and so we just like powered through so quickly. So what about an example of what this actually looks like? So if you have a situation where, so remember what the divergence operator did. What it did is it looked at the details of how it works. Is it looks at how the vector field, how the x component of the vector field is changing in the x direction, and then it adds it to how the y component of the vector field is changing in the y direction, and then also for z. But if you just do it in 2D, if you have something like this, so say you've got a situation like that, so here's our little set of cells where we're doing the calculation. So if you look at how the x component of this vector is changing in the x direction, well, it's not changing. And then we look at how the y component of this vector is changing in the y direction. Well, it's 0 in both cases, and so it's not changing either. So in this case, the gradient of the divergence of the E field is equal to 0. So that's a simple one, but there's other, more complicated ones that could also have a divergence of 0. And so one example is, say we've got, so here's our grid. So say we've got something like a circulating field. So say the vector is like that, and then it's like that. And then, over here, say it's a kind of a circulating field. Vector is like that. So let's try this divergence on this guy. And so here what happens is if we look, so we got to break these vectors up into their components. So we're comparing basically this guy to this guy and this guy to this guy. So if we look at here how the x component is changing in the x direction, it's not changing, that's 0. But here if we look at how the y component is changing in the y direction, oh no, sorry, I did that wrong. Right. Best laid plans. So this guy is actually going to be a little bigger. Because imagine if you've got like sort of some circular field like this of vectors. So what will happen if you have a perfect circular field of vectors, the y component will be the same, and in this special case, the x component will be the same because the x component is 0. So it turns out if the vectors are all in the same direction, the divergence is 0. If the vectors are in a perfect circular pattern, the divergence is also 0. So the divergence of that E is 0, but it's also 0 here. And so why would the divergence, what is the situation where the divergence would be big? It would be a situation like something like this. So where the vectors are spreading out like that. So in this case, what happens is the x component gets a little bigger in the x direction, and the y component gets a little bigger. So this gets a little bigger here, and this one also gets a little bigger here. So in that case, the divergence equals positive. So that's the kind of thing that we're trying to detect. And so we're trying to sort of detect, are the vectors kind of in this locally? It's all local. It's just at a point, and just look at your neighbors. So when you look at your neighbors here, if they're circulating sort of circularly around you, the divergence will be 0. If they're kind of like spreading out, sort of like fanning out, they're radiating, the divergence will be positive. But they could also be sort of contracting. So you could imagine a situation where they're all sort of like aimed in a little bit. In that case, you get a negative divergence. That would indicate that right at that point, even though, so you can see it's a little subtle because these vectors are all, they're all sort of like about 45 degrees. But in spite of the fact, that indicates that this is a radiating field, whereas if you had a situation like, something like this, where these guys were, slightly in like that, that indicates they're still all about 45 degrees, but this guy indicates that the divergence is negative. And these are very simple cases. In real life, the vectors could be in any direction, and you could still calculate what the divergence was, and then you've got to deal with 3D, right? It's sort of sticking in and out. So there's kind of a lot of bookkeeping to do. But basically, the way you end up calculating this is really simple. It's even you don't have to deal with vectors, or you don't have to deal with sort of x component of the x component. All you have to do is just do this thing right here. Just compare yourself. Subtract the average of the neighbors off of yourself, and then you're done. So that's kind of like the sort of mathematical magic there. So this is the introduction to the Maxwell equations. We didn't really describe it in enough detail. If you look at a physics book on the Maxwell equations, you'll notice there's a couple extra letters. So there's I'll put them here. We'll just introduce those other letters, because sometimes you see instead of the magnetic field for B, you end up with an H. So here's some of the main letters. So we have the current density. That's just like the actual vector. What direction are the currents moving, and that's equal to the conductivity times the E field. So E and J are related to each other. But then there's an H, and the H is the magnetic field. But it's the magnetic field accounting for how sort of magnetizable so that one's called the permeability. So are you in a piece of iron, which is like really magnetizable, or are you in air? And so that constant is multiplied by the B field. So the B field, so that's kind of like, you can sort of think of it as like magnetic resistance, or the inverse of magnetic resistance. And then there's also a D. And the D is just equal to yet another constant times the E field. So this guy is called the permeability, which relates to how magnetic fields go through things. This was the conductivity. And this guy was called the permittivity. Okay, so all these. So when you first look at this, there's all these letters. It's just like, what do all these letters mean? But there's the main one. So we have the magnetic field, or we have this kind of bulk magnetic field after you consider what type of substance it's in. And then you have the electric field, and then the current density, which direction does the current go, depending on how conductive it is. And then you have this D field, which is also just a constant times the electric field. So sometimes the Maxwell equations are written with E and B. Other times they're written with H, and D. But those are sort of somewhat similar. So we're all going like ridiculously too fast, but that's okay. You just need some harsh introduction to all the main letters, and then you have to do it 50 times over to actually understand it. So it was just sort of like just an introduction to what we're going to talk about next week. So next week I'm going to talk about how you actually use these equations to essentially get a forward solution. So if you've got some sources and sinks in the brain, what would we expect the currents to be on the outside of the brain? And you use these equations to derive those currents to sort of figure out how you go from perpendicular to the cortex flow of currents, which is the main effect is why we call it a current dipole, how you go from that to an actual electrical current coming out of the scalp, or a magnetic field, the magnetic field vector coming out of the scalp. And then on Wednesday we'll talk about how do you go from those measurements on the top to try to figure out where the currents were. So that's the forward solution. So the forward solution is you've got a J down here, and then you've got a potential here, but you've also got a B vector here. So that's the forward solution. How do we get from sort of J to B and voltage? And then the harder one is the inverse problem. And so the inverse problem is, how do we get from, we've got some voltages out here, and we've got some magnetic field vectors out here. How do we try to predict where all the current vectors are? Okay, so this guy is on Monday, and this guy is on Wednesday. Okay, so let's stop the recording there, and let's take a few questions.